In this video, we're going to talk about the goodness of fit test. Goodness of fit test is also called the one-way classification problem for enumerative data. For example, the classification of people according to the responses to the question, do you like this course? With k equals to 3 options. And the 3 options are yes, no comments, or no. Another example is to classify people into k socioeconomic classes, which would give counts or frequency to each classes. A random sample of n equals to 200 people from a certain district, say from the Peak, which is known to be a residential district mainly for the rich people, use the following data. 3 classes, namely upper denoted by 1, middle denoted by 2, and the lower class denoted by 3, with a total of 200 people. We have observed O1 equals to 50. That means the number of people in the sample from the upper class equals to 50, and O2 equals to 110, O3 equals to 40. O1, O2, O3 are also called the observed frequencies of the I cell, of cell 1, cell 2, and cell 3. And mathematically, we let Pi be the probability that a randomly selected subject will fall in or belongs to class I. And hence, sum over all the probabilities, Pi for I from 1 to k must be 1, because a subject must belong to exactly one of the k classes. In our last example, suppose we know that P1 equals to 0.2. That means the proportion of upper class people in the population equals to 0.2. And P2 equals to 0.45 and P3 equals to 0.35 for the Hong Kong population, according to the Census and Statistics Department. A question of interest is whether the socioeconomic status distribution at the Peak is similar to that of the general population in Hong Kong. And how can we perform the test? We can carry out the test by a so-called Pearson chi-square test. And statistically, we are testing the null hypothesis that the proportion of upper class people at the peak equals to P1 peak equals to P1 node. And this hypothesized value is known to be 0.2 because we are comparing this with the Hong Kong population proportion. And P2, the proportion at the peak, the proportion of middle class people at the peak equals to P2 naught. The hypothesized value equals to 0.45, which is the value of the Hong Kong population. And P3 peak, the proportion of lower class people at the peak equals to P3 naught equals to 0.35, which is the population value of the Hong Kong population. Then we have the alternative hypothesis, and we now have a very simple alternative. We simply state that the null hypothesis is not entirely true. It could be the case that P1 equals to 0.2, but P2 not equals to 0.45 and P3 not equals to 0.35. But it is a very complicated scenario, so we simply state that the null hypothesis is not entirely true. Other common examples of the one-way classification problem would be testing for the hypothesis that a die is a fair die with k equals to 6, or a coin is a fair coin with k equals to 2. The goodness of fit test is actually a statistical test for the cell probabilities, as what we have here, testing for the 3 cell probabilities. And the Pearson chi-square test is actually a very powerful tool in making inferences about the cell probabilities, P1 up to Pk. And in 1900, Carl Pearson proposed the test statistic, and we call this the Pearson's chi-square test statistic, x squared, equals to sum over I from 1 to k, and we have OI, the observed frequency of the I cell, minus EI, the expected frequency of the I cell, taking the whole square and then divided by EI, the expected frequency of the I cell. And EI is the expected frequency of the I cell under the condition that the null hypothesis is true. And notice that we have sum over the OIs, I from 1 to k, it must be n, the total sample size. And also sum over the EIs would also be equals to n. And when n is large, the statistic will possess approximately a chi-square distribution in repeated sampling under the null hypothesis. To test the null hypothesis that a die is a fair die is equivalent to testing the cell probabilities. That the null hypothesis is that the 6 proportions are all the same. P1 equals to P2 equals to P3 equals to P4 equals to P5 equals to P6. And to make sure that the 6 probabilities will add up to 1 and the hypothesized probabilities would be 1/6 for each of the 6 cell probabilities. If the die is tossed n equals to 600 times, what would be the expected frequencies for each of the 6 cells? And the answer is very natural and intuitive, which is 100. Because the expected frequency of the ith cell is simply n, which is 600 multiplied by their hypothesized proportions under the null hypothesis by common sense. So each of the EIs would be simply 100 in this particular example. For example, the data, it may look like this. If we really toss a coin 600 times, and the expected frequencies would be 100, 100, 100, 100, 100, and 100, because they are all equal to 600 multiplied by 1/6. But the observed frequency, because everything is random, it will not obey exactly. And the OIs, for example, O1 will not equal to 100, but it will fluctuate around 100, even though the die is a fair die. So, for example, this is what we have, the data. This is what we actually have observed. And the question is there evidence to suggest that the die is loaded, such that some outcomes will occur more frequently, or that is just due to chance? And using the Pearson chi-square test, the test statistic is simply sum over the OI square. For example, when I equals to 1, we have 107 minus E1, 100, taking the whole square divided by E1. And similarly for I equals to 2, 3, 4, 5, and 6. And we can simply calculate the test statistic to be 9.98. A large value of the test statistic is in favor of the alternative. But the question is the test statistic equals to 9.98 large enough? Okay. So to answer this question, we will first consider the characteristics of the test statistic, and that will be discussed in the next video.